let's talk about quantum computing. I think many of us have a good idea of how computers work in general. It's all about taking zeros and ones and manipulating them, performing calculations with them. And this is used everywhere. We do it all the time, everything from completing our tax returns to modeling some of the more complex industrial processes that we study within Capgemini engineering. Now, quantum computers are not so different. They involve quantum bits or qubits, and they look like this. We've added the funny brackets to identify that these are quantum states. Now, where quantum states or qubits are a little bit different is that they don't have to be just 1 or 0. They can be in states like this, a bit of 0 plus 1, or maybe 0 minus 1, or indeed any amount of 0 and 1 in what's called a superposition. Now, this is a fun party trick, but with just a single qubit, it's not so obvious how this is valuable. But let's instead look at the situation of 20 bits and 20 qubits. Here are 20 bits. You see we've got 20 ones and zeros. That's what we have. If we have 20 qubits, the state in general looks something like this. It's all a combination of all of those orderings of zeros and ones, each with different amplitudes. You see them listed down the side, A1, A2, A3, and so on. How many amplitudes are there? Well, with just 20 qubits, it turns out there are 1 million such amplitudes. Million amplitudes. What about if we were to double our number of qubits? What if we have 40 qubits? Well, it turns out then there are 1 trillion amplitudes. And you may be able to see where this is going, this exponential growth. By the time we get to, say, 300 qubits, we have more amplitudes than there are particles in the visible universe. So what does this tell us? This tells us that there is no way that any conventional computing hardware could begin to simulate the state of a quantum computer already at this scale. Now, this alone doesn't tell us that this is useful, but much of the magic in creating quantum algorithms is about being able to perform manipulations on qubits, which take advantage of that huge space of all of those amplitudes. And the sorts of applications are in simulating quantum complex systems, optimizing tough problems, and even bringing in a new era of AI with quantum machine learning. Now, quantum computers are not going to solve everything. We're probably never going to check our emails with a quantum computer, but what we probably will do is start to use them for some of the tough engineering challenges out there.